Got my parts back from Henrico Tool, the slide valve and the balance piston. Let me show you how those turned out. But first I want to pick up where we left off on the action of the slide valve in the steam chest and the timing events that surround that. Okay, I have the engine set up with the governor relaxed, so we'll call that wide open throttle. It's maximum stroke. The engine is at front dead center. I have two cameras. I'll keep this camera set up on the flywheel to show you where we're moving it. And then I have camera 2 set up, zoomed in on the slide valve. And we want to start out and remind everybody that this is the direction the flywheel is moving. Counterclockwise. Now when you look at the cutaway view of the slide valve, if this were a normal engine, basically the steam chest is at 150 psi, and because the leading edge of the slide valve has pulled back, exposing the pressure port, you can see that we have about 1/8 of an inch overlap. Steam would be going into the front end of the piston. This port pressurizes the face of the piston. This port pressurizes the back side of the piston. Simultaneously, the back side of the piston, that port can vent through into the center cutaway of the slide valve, and this big open area in the center is the exhaust. So this is at zero pressure. This is at zero pressure because they're connected. This port is connected to the inside the steam chest, so that's at 150 psi. But what I want to do is I want to move the engine back and forth until we just get the point where that edge starts to emit steam to the front of the piston. And unfortunately I can't see it when I'm working the flywheel, so I might have to do a little bit of jogging back and forth, but we'll get it as close as we can, then we'll make some marks on the flywheel. Now to me, that looks like this leading edge is exactly starting to pull back from the leading edge of the port. And as you can see from this mark on the flywheel, we're before front dead center. The flywheel is moving in this direction, but when we get to this point, the pressure is beginning to be admitted into the piston. So we'll put a mark on that. And we're going to call this mark, we'll call it intake start. So IS, wide open throttle. Now what we want to do, we want to roll the engine around in the direction that it is running. What you can see is that port opening is getting bigger and bigger. Now at this point, our front dead center mark is basically approaching 90 degrees of rotation from the top, and our port is still open. So we want to keep rotating it until the port just starts to close off. Looks like about 1/16 of an inch to go. That's actually a little bit too far, so we're going to back it up a bit. We'll call that good. So the engine has turned almost exactly 90 degrees. And that means that the piston is halfway down the cylinder, and we have now shut off steam to the front end of the piston. And so from this point, that pressure that exists in the cylinder, which is 150 psi, is going to have to expand because we're not admitting any more steam into the cylinder, so it's going to have to expand and the pressure is going to start to decrease. Meantime, the other side of the piston is still venting to atmosphere, to the exhaust. So in terms of cutoff, they talk about the cutoff of a steam engine in the percent of the stroke, and this is a 50% cutoff because we've gone for 50% of the stroke emitting steam, and we need to mark on the flywheel intake. We said start, intake closed, wide open throttle. So we've gone from here to there, slightly more than 90 degrees. Let's just continue to roll this around. Now you can see that we're exhausting the front of the cylinder, and the rear half of the cylinder is approaching a point, and we're now admitting steam to the back side of the piston. Now, there's a whole discussion about the placement of these valves. They have to be exactly centered on their travel so that they travel past the intake port the same amount on this side versus on this side. I don't know, and I haven't checked to see if this engine is balanced. We're just using the positioning of things as it is for now. And another thing that I noticed when I looked at this slide valve is this face is not as long as this face. And that's by design. Now, I thought it would be symmetrical. And then I thought, well, why would they make them asymmetrical? And then it hit me. The area of the cylinder on the front side, and the area of the piston on the front, and the area of the piston on the back are not the same, because you have the piston rod coming through packing, and you do not have the area of that piston rod to apply pressure to. So what they've done is they have lengthened the valve face on this side, which delays this half of the cylinder from exhausting. So the pressure stroke that this valve creates has a duration here, and it has a slightly longer duration here. And that is to make things average out, so you have the same amount of net force on one side of the piston as the other. So what I want to do at this point is I want to crank the governor to the closed position, and we're going to watch what happens with that face right there. Okay, so I have not rotated the flywheel, and we're at the point where the intake stroke would start. Now we're going to crank up this governor and reduce its stroke. Wow. Well, I'll tell you what this tells me is if this governor goes all the way up against its stop, the slide valve is able to reduce its travel to the point where it doesn't emit any steam to either side of the cylinder. So I'm going to relax this a couple of cranks. Get back on our timing mark here. Let's try right there. So we're not admitting steam yet. Looks like we're just starting to admit steam now. If you look up here, we've changed our intake point to the left side of front dead center to the right side front dead center. And so that is intake start. And we'll just say governed. And we're going to see how much fewer crank degrees we have available to admit steam to the engine. We're open a little wider. Looks like we're closing off already. And we're already closed. Let's back that up a bit. I'd say that's dead on. Okay, so we went from intake starting at wide open throttle to intake closing wide open throttle. That's 90 degrees. Now we went from intake starting governed to this point here, intake closed, governed. So that's maybe, I don't know, 30, 40 crank degrees. And we have room to go. In other words, we could crank this down and that window would get even smaller. So the less amount of time that steam is available to go into that cylinder, the lower the average pressure is driving the piston. It's the same result as a flyball governor, reducing the maximum pressure to the engine, but doing it this way, we're not losing any efficiency because we're doing all that expansion in the cylinder itself. Well, I'm going to tell you something about crankshaft style engines that some of you may not be aware of, and that's that the two halves of the stroke are not equal. And by that I mean, let's look at the geometry of the Skinner engine. I was able to measure everything on this engine pretty easily. It's 55.5 inches from the center line of the crank to the center line of the cylinder. We have a 30-inch connecting rod. We have a 24-inch piston rod. But the only thing I don't know is the exact thickness of the piston. So I'm assuming it's 3 inches. Now with a 12-inch stroke, we have 6 inches on one side of the stroke and 6 inches on the other side of the stroke. And you can see by the crank that when you lay that out, the connecting rod does not intersect the crank, and the crank is not at 90 degrees. So that is the midpoint of the stroke. And yet we're 5.74 degrees off of midpoint of the crankshaft throw. So the differences between the two halves of the stroke. We have the top half of the stroke is 168.5 degrees, and the bottom half of the stroke is 191.5 degrees. It's a huge difference. That is why on the slide valve, the two faces of the slide valve are a different length. We have to have a different lap or a different duration on the slide valve for when it's admitting steam, because we have a long half to the stroke on the back half of the piston, and we have a short half of the stroke on the front half of the piston. When we change the dimension of the connecting rod, this discrepancy only gets worse. If the connecting rod were theoretically infinitely long, then this would approach zero, but watch what happens as we shorten the connecting rod. So with a 22-inch connecting rod, we're up to 7.8 degrees from 90. And the stroke differences go from 164 degrees to 195 degrees. So this geometry is important, and it relates to the placement of the piston in the cylinder and the percentage of cutoff that the slide valve is admitting steam to the cylinder, to the two halves of the cylinder. I also modeled the entire valve train geometry with the stroke of the eccentric, both at wide open throttle and at the fully governed position. 36-inch eccentric rod, a 17-inch offset rod, and then linkage up to the slide valve. And so this mechanism oscillates and moves the slide valve back and forth across the ports, which are fixed. This is actually linked to the connecting rod diagram that I just showed you, and so that they move in unison. I just broke the link so that you can see how this moves. And this is going to help me analyze the exact valve timing events on the engine when I do modify the eccentric to go from that large babbited eccentric to a spherical roller bearing. So just another exercise in SolidWorks I thought you'd find interesting. We took the slide valve and balance piston over to Henrico Tool Die to be surface ground. Started off with the slide valve and we put it face down on the magnetic chuck. The reason I did that was that face surface of the slide valve, that's precious. I didn't want to be grinding, 20 thousandths off of that thing if it was out of parallel with the back of the slide valve itself. So I wanted to dress a surface as flat and parallel to that as I could to start with. The face of the slide valve is hardened, and there's a hardening process that you can use on cast iron that makes the surface extremely wear resistant. And boy, we found that out in grinding this thing. It took better part of 4 hours of grinding and a lot of dressing on the wheel. That wheel would load up pretty frequently. You probably didn't have an ideal wheel for cast iron, but we spent a lot of time dressing that and then going back and forth and getting that surface flat within a thousandths until I'd say it was 95 to 98% cleaned up. Got a tiny bit in the corners that we didn't go after when we were done, but it is flat, and I can use it as a lap for the valve ports in the actual cylinder head casting. Working the back side of the balance piston on a lapping plate just to see if it's uniformly cleaning up. And I believe it is, because there are lathe marks on it where it was turned, and in most of the areas I'm seeing that I am cutting the lathe marks all the way around. There's a couple little high spots. I'm thinking maybe this is good enough just to put this surface down and then grind the face. So our balance piston has variation from the lowest point to the highest point of about 15 thousandths. We went and worked on the backside and cleaned up what would amount it to be a few little high spots until this sat pretty nice on the inspection slab and we couldn't get any rock. And we were just passing the other face under the indicator to determine how much. So this thing definitely has a kind of a wave to it, but it's not going to suck down, if it does, no more than a thousandths from the backside. I don't want to dress the backside to this because it's so far off, because the bore should be perpendicular to this back face, and we'll just cut this until it cleans up. Even if we got to take 15 thousandths off, it is what it is. Still working on the back side of the slide valve to get that to fully clean up, and that was about 8 thousandths off. Final pass on the back side of the slide valve, I'd say it's about 90% cleaned up. We have areas that have cleaned up all the way around, so when it sits, it's going to sit solidly for 360 degrees. No sense in just keep cutting it further. And we'll flip this boy over and start working on the face. Yeah, I like that.
This high, right? Like this.
Yep, that's the way. So let's keep track of how much we cut off of this
Oh, okay.
Because I'm going to have to go and deepen that step same amount. We got 10 here. I'm going to have to take that step down 10 later. Is it pretty straight?
Pretty much straight, yeah. See it, clean up the...
Okay. If you listen to the sound that the wheel's making, it sounds kind of rumbly, and this was before he dressed it. The back side of the slide valve wasn't very hard, but this face is really hard, and so we had to dress it multiple times to get through grinding the face of this slide valve.
You won't touch the this side?
No, that all has to be flat. The whole thing, yeah, the whole thing. The y-axis feed wasn't working on this grinder, and so what he was doing was, grinding in one spot, taking down, I don't know, 3-4 thousandths at a time, and then manually stepping it over and dressing the next area until it matched. It made me nervous, but he's good because when it's all said and done, this thing was flat within a thousandths over the whole surface. Final pass, walking it back across. Here's my balance piston back from Henrico Tool Die, and this surface is flat and parallel with the backside within a thousandths. You can see that I didn't get 100% cleanup. Got a tiny bit here on this end that was not cleaned up fully, but there was a 15 thousandths variation in this, and I just didn't want to keep grinding it. This surface is hardened somewhat, and the deeper you go, the more likely you run into getting into a softer zone. So I just called it quits when I saw that we had good bearing all the way around. Now, if you look closely at the ID, you can see and feel witness marks where the piston ring is sitting. They get fairly deep. They get probably, I would say, 5 thousandths of an inch deep. It's maybe even closer. We should put an indicator on that and see. But being that we ground everything, the piston ring is going to be sitting in a slightly different area. By the same token, you can see that the top surface of the piston is not perfectly flat. This side is better. This was the side that was against the backup ring. Maybe if I just flip this over, it would be better. This would be a difficult part to try to improve. you'd have to make some kind of a fixture to hold it to grind very slightly on the OD. There's two backup rings that have an L-shaped cross section. These are both cast iron. And one of them has this interesting feature, which is an anti-rotation pin. I don't know how it's attached. Must be drilled. There must be a drilled hole in there, and that pin is pressed into the hole. But that serves to anchor the piston ring and keep the piston ring from turning. That does just like that. And then all of this fits into the piston. And it's a pretty light fit. Of course, everything has to be perfect. You know, I'm going to have to do this upside down in order to make it work. So there's the backup ring. Backup ring with this little post and the one-piece piston ring on the outside. There are 4 pressure springs to hold the balance piston against the steam chest cover. I don't know, there's maybe 20 or 30 pounds to compress them 1/4 inch. You could still see the paint that is on these. Those springs load into 4 counter bores in the back side of the slide valve. And then there is a drilled passage in here that goes in, and then a vertical passage that intersects. So those two are connected. And I don't know if you can see it. You see that witness line right there? That's a plug. So these passages were put in from the top and probably before the groove was there. So it was drilled from the top and then plugged to intersect that hole down there. The backup rings load into the slot like this. And then the piston is expanded by hand. Doesn't take much. And it drops into the groove like that. So that's all the pressure there is holding that slide valve against the steam chest cover. This pocket receives the push rod and its flat driving disc. So that's pushed and pulled like this. This is the face of the slide valve that was resurfaced. Not 100% cleanup. Just I don't know. Didn't want to go any further than necessary. All of the valve action comes from this edge and this edge, and those have cleaned up 100% well past the port's end about here and here. And the rest of this is just a bearing surface for it to ride on the inside face of the steam chest. I put up a whiteboard to help do some of these explanations, similar to another one you might see. Yes, mine's bigger. Let's look at a cross-section of the entire steam chest assembly and the cylinder casting. So this is the slide valve, which moves back and forth. This is the exhaust port. This area is the pressurized, let's call it the supply, and this is at 150 psi. This entire area is pressurized. There's a spring in this little pocket, 4 springs, that are pushing the balance piston in green up against the face of the steam chest cover. And simultaneously, I guess, pushing the slide valve against the face of the cylinder, the ports. There's this little drilled passage in here that is open to the 150 psi cavity. And so this area right in here is pressurized to 150 psi. Comes in behind the L-shaped backup rings and against the back side of the piston ring, which rides on the inside. And it pushes the piston ring against the surface of the balance piston and against the top of the groove in the slide valve. So we're attempting to make a seal on this face right here. So zooming way in on this, we have our steam chest at 150 everywhere on the outside. And we have the exhaust at 0 psi everywhere here. There's a few thousandths gap between the guide post on the slide valve and the balance piston, but it is free to rotate, and because this is a translating mechanism, this thing actually slaps the balance piston back and forth as the slide valve moves. This side is going to be, the gap is going to be swapping sides, carrying the balance piston with it. The backup, the piston ring, is attempting to maintain a seal against the balance piston, so it's going to be carried with it, and the pressure is going to be forcing it up against the groove in the slide valve, but it's going to tend to oscillate back and forth as well, and you can see evidence of wear along that surface, and then evidence of pitting and wear along the inner surface of the balance piston. This passage here, the drilled passage, there's actually 2 of them. So they're pressurized. They're about an 1/8 inch in diameter. And so as much air as can come in through 2 1/8 inch passages and pressurize this area behind the piston ring, as long as that area is greater than the leakage path across any irregularities here, then this will remain pressurized. But in the state that the parts are in right now, there's going to be some leakage past this piston ring. There's going to be some leakage past this surface on the top. These are not perfectly smooth lapped finishes. And what I was experiencing when I tried to run the engine initially was all of these were way more area than these 2 patches could keep up with in supplying pressurized air behind this. Hoping that with this reconditioned and the face of the slide valve reconditioned, that's going to be enough to get the engine to run. But the top surface of the balance piston had a 15 thousandths variation in it, and it wasn't there was a high side and a low side. It was kind of wavy. It had high spots and low spots from traversing back and forth across the inside of the steam chest cover. And the face of the slide valve also had about 8 thousandths variation. So hoping to lap this in on the steam chest itself. Dave Richards refinished the face of the steam chest cover within 1 thousandths. When I put this all back together, I'm hoping to have the leakage under control to where my 5 horsepower Quincy air compressor can keep up with it and actually get this engine up to some RPM. Don't know if I can get it up to 300, but it would be nice to get it up fast enough where the governor could begin to actuate, reduce the stroke of the slide valve, and start conserving the air that goes through the system. Well, I hope you enjoyed that. I am going to put the slide valve assembly back in the steam chest I'm going to try to lap the surface of the steam chest, because even though the slide valve is flat, the balance piston is flat, and the steam chest cover is flat, the actual port area of the steam chest probably has as much variation as the valve itself. So being that the valve is perfectly flat, I'm going to use that as a lap with some abrasive sheets in between and try to get that surface cleaned up better. And then we'll try to run it. We'll see if we can get some decent RPM out of the engine. Meantime, I will move on and start talking about I believe I'll start talking about the crankshaft area, the main bearings, and the ways that guide the crosshead slide next. So thank you for all the new subscribers. Hit the bell notification if you want to get updates as to what we're doing in the shop. And once again, thanks. Catch you next time on Engineers Workshop.